Building a nuclear facility in a seismically active zone forces engineers to solve one of the most difficult problems in modern physics: surviving massive earthquakes. The primary objective of nuclear seismic design goes entirely past keeping the concrete wall standing. The specific, non-negotiable mandate is preventing radioactive material from escaping into the environment. To achieve this, the facility must successfully execute a rigid triad of safety steps: shut down the reactor, cool down the core, and contain the radiation. The consequences of failing any one of those steps are severe. The 2011 Fukushima disaster demonstrated exactly what happens when extreme natural forces overwhelm a facility's defense systems, exposing the sheer destructive reality of these events. Achieving zero radiation release against unpredictable natural violence relies on a highly formalized, multi-tiered engineering methodology. Before a single yard of concrete is poured, geologists excavate the site to read its specific geological history. They map the strata and search for hidden active faults. This physical data feeds into probability models to calculate a worst-case scenario metric known as the design basis earthquake. This baseline metric does not represent an everyday tremor. It is an extremely rare, mathematically derived event engineered to account for a 1 in 100,000 year probability. Engineers translate that scenario into a specific seismic wave, defining its force at the rigid bedrock layer. As the wave travels up through looser surface soil, its destructive amplitude multiplies right before it strikes the plant's foundation. Without precise geological measurements of that soil amplification, any structural design built on top of it is effectively guessing. A fully operational nuclear facility requires thousands of individual systems spanning dozens of acres. Making every single pipe and turbine equally invincible is physically and financially impossible. The regulatory solution is the Seismic Importance Classification. This is an engineering triage system that assigns structural rigor strictly based on the risk of radiation exposure. Lower tiers, like C-class and B-class, cover general structures and are built to standard codes or given a 1.5 times strength multiplier. The highest tier is S-class, reserved strictly for the reactor core and critical cooling systems, hardware that absolutely cannot fail. By classifying equipment this way, regulators ensure massive engineering resources are hyper-focused exactly where a structural breach would threaten public safety. Regulators subject all S-class equipment to a rigorous dual-pronged mathematical assault on paper, beginning with static force. Static force calculations apply massive brute force multipliers. S-class structures must withstand up to 3 times the steady seismic force dictated by standard building law. But an earthquake is a violent, chaotic motion, so brute strength is insufficient on its own. Engineers must also test these structures against dynamic forces using 3D wave simulations. Here we see the sway rocking model. This simulation accurately maps how the immense weight of the building interacts with yielding soil, calculating both rapid horizontal shaking and severe vertical drops simultaneously. Surviving a severe earthquake demands structures that are incredibly rigid against heavy static loads, yet intelligently resilient against unpredictable three-dimensional dynamic waves. For decades, the industry treated the calculated design basis earthquake as the absolute ceiling of nature's power. Reality proved that nature will eventually exceed humanity's best mathematical models. Global engineering standards now require plants to design for the beyond design basis earthquake, a tier of destruction that pushes past calculated limits. The explicit goal of these protocols is stopping cliff edge effects. This happens when a slight increase in shaking beyond the design limit causes a sudden catastrophic failure of the entire system. Engineers neutralize these cliff edge effects through extreme redundancy. They install diverse backup power sources, alternative cooling systems, and advanced shock absorption layers that immediately take over. Global watchdogs like the International Atomic Energy Agency standardize these safety margins, enforcing a strict baseline of extreme resilience worldwide. Securing a nuclear reactor against seismic threats is a continuous process of pushing safety margins further outward to stay ahead of unpredictable natural chaos.